Hello, my name is Ryan McBee, and today I will be discussing a research paper that focused on attack detection in water distribution systems using machine learning. So, a bit of an introduction to this project. The research group that wrote this paper were focused on detecting attacks on a hypothetical water distribution plant. And the motivating factor behind this research was an increase in the number of attacks towards water distribution plants over the last few years. If you look at the chart on the right, you will notice that in 2013 there was around 13 attacks. But go to 2015 and there are 24 attacks. So the number of attacks on water distribution systems, which are typically a very critical system in our cyber-physical infrastructure, is increasing at an alarming rate. And many of these attacks are not just attacking various sensors. They can also come from disgruntled employees. And so a detection system for these anomalies needs to be devised that can kind of handle all the different scenarios that can cause attacks on this type of system. And so what this team and what a lot of detection methods for this type of system rely on intrusion detection systems. And there are two different types of intrusion detection systems. There are signature-based systems. These are detection algorithms that rely on pattern matching. And so if you've seen an attack before, such as a compromised sensor that goes to zero, like someone has cut the line, then a signature-based system would be able to see that, and based on a set of rules that it has seen before, it is able to detect these anomalies. And because it's so simple in its design, these detection mechanisms are actually very fast. But the unfortunate part is they don't handle attacks that have never been seen before. And so in many of the cases, they are just not as useful. And this is in contrast to a behavior-based intrusion detection system. These systems use advanced algorithms to model the behavior of the system by either looking at the sensors, the actuators, or a combination of all of them to detect what is a normal behavior. And based on the algorithm, there then is some way of distinguishing the output of these algorithms to say, is this a normal in the normal behavior model, or is this outside or an anomaly detection? And this is where this paper focuses on for its research. So the goal of the paper was to compare a variety of popular anomaly detection algorithms and discuss and debate their applicability. And in particular, they focused on a competition that used the BATADAL dataset in competitors as comparison. This dataset in the competition focused on a fictitious water distribution system and has various different competitors to compare their algorithms against. So this paper is trying to evaluate conventional anomaly detection algorithms against the competitors and against themselves. And then in this paper, they also propose a novel ensemble detection system, which I'll describe more in detail later. And so before I get into some of the algorithms that this research team focused on, I'm going to talk a little bit about the data set that they were analyzing and using for their detection. So the BATADAL dataset is a dataset that was made to promote cyber-physical security and detection of anomalies. And to help promote this, they used a competition which competed different groups to detect attacks on a fictitious water distribution network. And within this dataset, they provided three datasets. There was a normal dataset of just plain data of the normal operation. There was a training dataset in which the labels were provided of when the abnormality or the anomaly was actually happening. And there's a test data set in which there are anomalies going on there, but there's no labels associated. And some of the flavor text along with this data set is this: it was part of this fictitious Seatown water distribution network. So, like I said, there were a bunch of competitors for this competition. The research group that did this paper did not compete in this, but they were exposed to some of the metrics that the competitors had used in their research papers and their methods. And by looking at them, they noticed that all but 2 of the research groups produced multi-stage detections, which I will talk about more later. But that seemed to be the very popular approach out of the 7 different teams. One of those teams, who did not use a multi-stage approach, actually used a simulation-based detection. And with the simulation-based detection, they used a simulation software that was used to model like water plants, the filling, the sensors, and using that to perfectly model this water distribution system, the Seatown water distribution system, and in comparing the results, anytime they deviated, flagging that as an anomaly, yielded actually the highest results out of all of the team. But the researchers here noted that even though this produced the highest results, this simulation-based technique grows ever more difficult as the system, as your cyber-physical system grows more complex. And they gave the example of a smart grid, which has large amount of distributed systems, can vary based on just a whole host of things such as user usage and other things like that, in which a simulation becomes much more difficult. And the other team that did not use a multi-stage detection used recurrent neural networks. And recurrent neural networks are networks that use data over time. So they are a time series based neural network approach. And so they split the data into tank level analysis, and then they trained recurrent neural networks to learn the temporal pattern that each of this data actually behaved over. So what were the reason why so many teams used a multi-stage detector? Well, one of the main reasons is they wanted to be able to detect content and contextual anomalies. And a content anomaly is an anomaly that happens on a very specific component and when it is not working. So in the instance of a water distribution system, that would mean a single water tank is not working or a sensor is not working. Whereas with a contextual information or anomaly detection, that is the entire system is not working. And in which case you can imagine one tank that flows into another tank that flows into another tank, analyzing all of the tanks at the same time when there is an issue with the releasing and flowing into another might have more rich data for these anomaly detectors to actually detect. So a lot of these groups split up the work in the anomaly detection to hopefully make it a much simpler problem. And so now I'm going to get into a couple of the anomaly detection algorithms that this research group focused on. And in the next few minutes, I will describe a bit more of what they are. But in a high-level overview, these anomaly detections can fall into the group of density-based algorithms, parametric-based algorithms, classification algorithms, and then ensemble-based algorithms. So what are density-based algorithms? Density-based algorithms are algorithms that take the data, which can be any dimensionality of any shape and size, and they apply algorithms to them, and hopefully to kind of reduce down the data, and then from there it will try and model the data in a meaningful way, such that data that matches what the rest of the data looks like will be highly clustered together, and then anomalies will start to kind of taper off in a further distance. And so 2 of these algorithms we'll be looking at are the local outlier factor algorithm, or LOF, or the subspace outlier degree algorithm, or SOD. And as you can see on the screen right now, the equations associated with both of them are underneath their respective algorithm. For the LOF, it assigns an outlier score, or how far away is the sample from the rest of the data. And so there are various metrics and various ways to tune this, but this general framework is what is used to actually designate that. And below that, the subspace outlier degree algorithm, its goal is it works better on higher dimensionality data, which is why it was looked for in here to kind of show the broad range of data. And so it will project a high dimensional data into a smaller hyperplane or a smaller amount of dimensionality, which is easier to process on. And points that deviate from this new hyperplane, so stuff that is unable to map into a specific area or cluster, is then considered an outlier. So both of these metrics try and form a model of what the data looks like, and then anything that deviates away from that will then be considered an outlier. So parametric methods, on the other hand, can go a step further in the amount of assumptions by making assumptions about the density and the distribution of the data. And one such algorithm, and excuse me if I butcher this name, the Mahalanobis distance, or MD, is very similar to the Euclidean distance that many of us know in a Cartesian coordinate system, but this algorithm also uses the variability in the correlation of the different variables to kind of account for its distance metric. And this type of algorithm is very good for much lower dimensionality data, but whenever you have a much higher dimensionality of data, collinearity can become a lot stronger, and the variance-covariance matrix of the data is not always invertible. And if you look at the equation in here, you can see within the square root in the middle that c subscript x to the -1 is the inversion of the variance-covariance matrix. And this, you can kind of imagine, if you have a linear algebra background, that the higher dimensionality this is, it A, becomes much more difficult to invert, but B, there's a chance that it might not be invertible. And if that is the case, then this algorithm is not applicable. And so that is one of the downfalls of using a parametric. But in many cases, the parametric, because of these assumptions, if it works, can actually lead to much stronger results than a density-based algorithm. The next category are classification algorithms. And some of you might be familiar with this, I am as well, that a lot of machine learning nowadays have focused on classification-based algorithms, a lot of your neural networks and of the like. In this research paper, they don't focus on neural networks. They tend to focus on much simpler statistical and other non-neural network-based algorithms for reasons that'll be apparent pretty soon. And so these algorithms, these classification algorithms, inherently use historical data to find a model to classify as normal or abnormal, very similar to the rest of the data. And for discriminant analysis, its goal is to basically see all of the data in front of it, and then the positive data and the negative data, and try and draw some form of line, some kind of boundary between these two. And the two types that are explored here are linear DA, or LDA, or quadratic DA, or QDA. And as the names imply, linear DA tries to take the data and form some kind of line or some linear combination that distinguishes between the positive data and the negative data, whereas the quadratic DA uses a more higher level polynomial to actually distinguish and build these boundaries between them. And the parametrics also use the MD from the previous slide to help separate the different classes. So this is a bit of an ensembling or pairing method that we'll talk about more later. And the DAs work very well when the data is a multivariate Gaussian, because then you can then, it has a very strong pattern that it can then distinguish between. And then the final one here is the one class support vector machine, or the OSVM. And the support vector machine, these are all very similar. The support vector machine is trying to find a boundary as well, but through different means. And so it is trying to draw a decision boundary around most of the positive points. And a Gaussian kernel, in which if you can think of a normal or bell curve distribution, works best as the kernel for how it is separating and saying how far are these data points from our normal. But using a Gaussian, because it has a lot more granularity, requires more data. And unfortunately, the OSVM, because it is a more supervised learning technique, has a lot more issues when it tries to classify positive data when you have a huge class imbalance, particularly in these anomaly detections. There's a huge skew to having more negative data where things are working normally and much less data on where things are going wrong. And this OSVM also works very poorly on high dimensional data, just because there's a lot more room and wiggle to play in, because it's a little bit more complicated, a little bit more advanced, whereas the discriminant analysis is just a basic separating line or quadratic approach, which has a much easier time even with higher dimensionality. But even the discriminant analysis starts to fail as the higher dimensionality grows. And so overall, what this research paper wanted to focus on was exploring whether ensemble techniques would be applicable in this situation. And an ensemble technique is one that combines multiple different techniques. And as were kind of briefly noted as I went through the different algorithms, each of these algorithms have a different strength and weaknesses depending on the dimensionality, the depth, the number of positive, the number of negative samples. And so you can see that combining these in either a 2 ensemble, a 3 ensemble, or some kind of other combination can have some benefits where one can make up for the downfalls of the other. And so in general, you can also, some notes to take away are the parametric approaches were found to work the best, but only when the distribution is known and the data was very low dimensionality. And so an example of a parametric approach was the MD, which required the covariance matrix, used a lot of that data, and so you can understand why it would like low dimensionality. But with QDA, works good since the decision boundary is more complex than the linear LDA. And using a QDA allows you to separate out the data and separate them out into different categories, which lowers the data. And then also using the density-based algorithms, they don't make any assumptions about the data. And they typically generalize better, but are less accurate. And in this specific example, when they applied the density-based algorithms to the data set, they actually found that the density distribution formed by these were actually a skewed Gaussian, which you can see as below. And the left graph is actually the LOF density distribution, where for an LOF, most of the data, if it's considered normal and not abnormal, it'll be a value as close to as 1 or just slightly above 1. And the higher it is above 1, the higher likelihood that the data is abnormal. And on the right, we have the SOD density distribution, in which this value actually varies between 0 and some positive number. And as you notice in both of these cases, both of them skew their data towards normal distribution, and as it kind of increases, it follows a skewed Gaussian distribution. So this paper proposed a novel ensemble technique. And so you take the input data, which in this case are the pressure sensors for the various different tanks within the system, and you feed this data into both the SOD and the LOF, which are both the density-based algorithms. These algorithms are going to form that skewed Gaussian that you saw on the previous slide. And now that you've reduced the dimensionality of this data into two values, because the output of each of these functions after it's trained and detecting is a value on how abnormal it thinks this data is, you can then feed this data into a QDA, which now that you've reduced the dimensionality down to just two values, this algorithm can perform much more strongly than if it was just processing the higher dimensionality data. And so the metrics for the competition were true positive rate, which is how well did you actually detect it actually being an abnormality. The false positive rate, which is how many times did you detect something when it actually was not an abnormality. The time to detection, or as soon as an anomaly was started, how long did it take for you to actually detect that. The CLF, which is the mean between the true positive rate and the true negative rate. And the metrics for this specific competition used a combination of the TTD and the CLF in equal parts, in which gamma in this case was equal to 0.5. And for comparison in a much more meaningful way, an F1 score was also used to assign, which was not used in the original data, but the authors noted that this is a very popular metric used in machine learning and would allow for better comparison and a much more meaningful metric, because the F1 score is a relatively balanced metric, which in a lot of times you can have an issue which is called the accuracy paradox, in which if you have a very skewed data set in which there's very few positive results and a lot of negative, you can have a very accurate result by detecting everything as not an anomaly. But an F1 score tends to kind of throw that imbalance out the door and is able to actually show you metrics that are more meaningful, such as how often are we actually detecting the true positives kind of comparatively to itself, so that data distribution skew is not nearly as much of an issue with this F1 score. So this is a lot of data on the screen, but if I'll direct you to the left side and to the left columns, the leftmost column is the rank. And so these are the various ranks of the competitors, and these new anomaly detections the research team proposed ranked from 1, meaning this was the best algorithm, to 15, which is the worst. And the metric that was used for this is the S-score, which the S-score was a 50-50 combination of the time to detection and the CLF. And so if you look at the next column for name, the way the names go down is it is either using the acronym for the anomaly detection, which was noted earlier in this presentation, or it has a B with a number followed by it. And these numbers correspond to the various competitors of the original competition, with B1 being the physics model approach, which has the highest score, with B7 being some unknown multi-stage detection that performed very poorly on the system. And one additional competitor in here is the naive approach. The naive approach is a very simple detection metric in which all they do is detect not anomaly. And as you'll notice, that has a relatively high S-score of 0.75, because you are constantly getting the negatives correctly. And so with all that data skewed, you are performing in a very naive approach, that whole accuracy paradox that I noticed earlier. And if you look at this metric based on their initial results, you can see that the OSVM, which I noted would perform very poorly, is less than the naive approach, which you have to look at multiple different metrics, because obviously the S-score is not a clear indication of how well it works, because an S-score that performs a 0.75 when it's not even detecting anomaly is not exactly the greatest in the world. And so, but below the naive approach is the outlier support vector machine, the linear discriminant analysis, and then the unknown B7 competitor.